The standard presentation of general relativity moves quickly through a distinction that deserves more attention than it typically receives. There is the Schwarzschild metric, Einstein's field equations solved for a spherically symmetric, non-rotating mass, and there is the Kerr metric, which extends the solution to a rotating one. The Schwarzschild solution is where most textbook treatments spend the majority of their time. Black hole anatomy, gravitational time dilation, gravitational lensing, event horizons, all of these emerge from the simpler, non-rotating case. The Kerr metric is introduced afterward, usually with a gesture at additional complexity, a note about ergospheres, and a brief treatment of what happens to orbits when rotation is involved. In the shape behind the symbol, the argument closed on a claim this essay takes as its starting point. That calling a mathematical formalism abstract is a statement about the perceiver rather than the structure, and that the geometric reality a formalism maps to exists regardless of our capacity to render it. The shapes are always there behind the symbols. The formalism points somewhere real. What follows from that is the obligation to ask, in each case, what geometric reality a given formalism is actually describing, not only what it predicts or what it governs, but what it is saying about the structure of the world. The Kerr metric is a case where that question has rarely been pressed. What is rarely asked is what the Kerr metric is actually saying, in geometric terms, what the mathematical difference between it and the Schwarzschild solution represents as a statement about the structure of the spacetime manifold itself. The difference is this. The Kerr metric has off-diagonal terms that couple the time coordinate to the angular coordinate. This is not a feature of the coordinate system chosen. It is a feature of the spacetime. In a non-rotating spacetime, the time direction and the spatial directions are cleanly separable. You can set up coordinates in which time is time and space is space, and the metric reflects this separation. In the Kerr spacetime, no such separation is available anywhere. The time direction and the direction of rotation are geometrically entangled as a matter of physical fact rather than a matter of formalism. This is what it means for a rotating mass to warp spacetime differently from a static one. The geometry has acquired a coupling that no non-rotating geometry possesses. The practical consequence of this coupling is what is called frame dragging, or the lens-Thirring effect, and it is one of the conceptually richest phenomena in classical general relativity. But the phrase frame dragging can make it sound like a secondary correction, an additional perturbation applied on top of a more fundamental gravitational effect. It is worth resisting that framing. Frame dragging is not a correction to the Kerr geometry. It is what the Kerr geometry is. The coupling between time and rotation in the metric is the dragging is the geometry. Where stillness fails, let me be precise about what frame dragging physically means, because the diagrams one typically finds in the literature, spiraling arrows around a spinning sphere, a rubber sheet with a vortex, convey an impression of flow without conveying the nature of what is flowing, or what it means for anything embedded in it. In a Schwarzschild spacetime, there is a well-defined notion of what it means to be stationary relative to distant stars. You set your rockets to hover, exert thrust to counterbalance gravitational attraction, and remain at a fixed angular position. The geometry allows this. Not rotating is a coherent geometric concept everywhere outside the event horizon. In a Kerr spacetime, this breaks down. Increasingly close to the rotating mass and past a specific surface called the ergosphere, which lies entirely outside the event horizon, the frame dragging becomes so intense that it is no longer possible for any physical object to remain stationary relative to distant stars. The constraint is geometric, not energetic. You may fire your rockets at full thrust in precisely the direction that would counteract the rotation. The spacetime still does not permit stillness. You must co-rotate. The only remaining question is how fast. General relativity introduces, to handle this situation, the concept of a zero angular momentum observer, a ZAMO. A ZAMO is defined as an observer with precisely zero angular momentum as measured from far away. By the ordinary intuition, zero angular momentum meaning not rotating, you might expect a ZAMO to be stationary. But inside the ergosphere, a ZAMO has a non-zero angular velocity. They orbit because the local inertial frame, the frame in which a local measurement would record them as not rotating, is itself rotating relative to the distant stars. They carry no angular momentum in the global sense. Their angular momentum reads zero because their local sense of not rotating has been dragged along with the rotating geometry. This is the point worth pausing on. Inertia, the resistance to acceleration that we typically treat as a fixed background property of spacetime, has, near a rotating mass, been rewritten by the rotation of that mass. What counts as not rotating locally is no longer determined by the distant stars alone. It has been influenced, structurally and irrevocably, by the spinning object nearby. The local geometry, which is what any freely falling observer experiences and which defines the inertial structure of that observer's world, has been altered by the geometry of what is near. The ergosphere is the surface at which this alteration reaches its extreme consequence, the elimination of stillness as a geometric option. But frame dragging is not limited to the ergosphere. It is present everywhere outside a rotating mass, at every distance, in every direction. The effect weakens with distance. As the lens-Thirring correction, it falls off as the cube of distance in the weak field limit, but it does not vanish. Every rotating mass is, at some level, rewriting the local definition of not rotating for every observer in its vicinity. The ergosphere is simply where that rewriting becomes total. The gravitomagnetic parallel. In the weak field, slow rotation regime, frame dragging acquires a structural analogy with electromagnetism that is worth examining carefully. The analogy has limits, but the reason it exists at all points somewhere worth going. In electromagnetism, a charged particle at rest produces an electric field. A charged particle in motion produces both an electric field and a magnetic field, the magnetic field arising precisely from the fact of the charge's motion, its current. The magnetic force is, in this sense, the relativistic consequence of an electric field applied to a moving source. Gravitation in the weak field limit has an analogous structure. A mass at rest produces what we recognize as ordinary gravitational attraction. A mass in rotation, equivalently a mass current in the same structural sense as an electric current, produces a gravitomagnetic field. This field causes gyroscopes to precess. It causes photons to propagate at slightly different effective speeds depending on whether they travel with or against the rotation. It causes clocks in retrograde orbits to accumulate time at rates minutely different from those in prograde orbits. None of these effects are large near the Earth, but they are real, and they have been directly confirmed. The Gravity Probe B experiment, launched in 2004 with results published in 2011, flew a set of extraordinarily precise gyroscopes in polar orbit and detected both the geodetic precession arising from the Earth's mass and the lens-Thirring precession arising from the Earth's rotation. The latter amounts to approximately 37 milliarcseconds per year, an almost comically small number by everyday standards, and nevertheless the signature of the Earth's rotation written into the local inertial frames of everything in orbit around it. The gravitomagnetic analogy is not merely pedagogical. In linearized general relativity, the field equations take a form that is structurally identical to Maxwell's equations with mass replacing charge. The analogy has limits. It breaks down away from the linear regime, and gravity is not a gauge theory in the same sense that electromagnetism is. But the parallel's existence and the structural reason it exists is a thread that the later parts of this essay will follow. What rotation asks of the universe? There is a question in the foundations of mechanics that Einstein inherited and partially answered. Newton's rotating bucket, the water rising at the edges as it spins, prompts the question, rotating relative to what? Newton's answer was absolute space, a fixed geometric background existing independently of any matter. Mach argued that this was wrong. Inertia must be caused by the large-scale distribution of matter in the universe. There is no absolute space. There is only matter and the relationships between it. General relativity's answer sits between the two positions, and frame dragging is precisely where the tension is most visible. In a universe containing only a single spinning mass with nothing else, Mach's principle would seem to require that rotating lose its meaning entirely, since there is nothing to rotate relative to. GR does not fully implement this. A Kerr spacetime can exist in isolation, and it carries a well-defined rotation parameter. The distant stars still define a reference against which local rotation is measured. But frame dragging represents GR's partial concession to Mach. The local inertial frame, what counts as not rotating at any point in spacetime, is not entirely fixed by the distant geometry. It is influenced by the rotating matter in the vicinity. In the limiting case of the ergosphere, it is overwhelmed by it entirely. The spacetime in the vicinity of a massive rotating object encodes the rotation of that object and writes it into the local definition of inertia. What we call local inertia is shaped by what is near, not only by what is far. This is a philosophically significant observation with structural consequences. If local inertia is even partially authored by local matter distributions, then the question of what rotating means anywhere becomes a geometric consequence of the entire matter distribution of the universe operating simultaneously at every scale, rather than a fixed background fact. The Earth's rotation imprints something on the inertial frames in its vicinity. The Sun's rotation imprints something on the inertial structure of the solar system. The galactic center, which hosts a supermassive black hole, itself rotating, of approximately 4 million solar masses, imprints something on the inertial structure of the galaxy as a whole. In general relativity, these contributions form a single geometric reality operating at every scale at once, irreducibly entangled, and the local inertial frame of any freely falling observer is, in principle, a consequence of all of them. The nonlinear tangle. This is where general relativity reveals one of its deepest structural properties, and where the intuitions available from Newtonian mechanics and even Maxwellian electromagnetism break down completely. Electromagnetism is linear. Two electric fields from two separate charges add. The principle of superposition is exact. Solving problems with multiple sources is, in principle, a matter of summing contributions calculated in isolation. General relativity is not linear. The Einstein field equations are nonlinear partial differential equations, and this nonlinearity is not a perturbative complication to be corrected at higher order. It is the content of the theory. It is what distinguishes a proper treatment of curved spacetime from a spin-2 field approximated on a flat background. The nonlinearity means that the spacetime geometry itself carries energy and momentum, and that this gravitational energy sources further curvature. You cannot add the metrics of two rotating sources and obtain the metric of the combined system. The combined metric is a new geometric object, distinct from any sum of its parts. For frame dragging, this means that the dragging effects of two spinning objects near each other are not simply additive. The frame dragging from each source modifies the spacetime through which the other's frame dragging propagates. The spin-orbit coupling, the interaction between each object's spin and its orbital angular momentum, has no Newtonian analog. In the strong field regime, as occurs in a compact binary of neutron stars or black holes, the two spins precess around each other and around the total angular momentum vector in ways that are nonlinear, irreducibly geometric, and that cannot be understood by treating each object's contribution in isolation. The gravitational recoil, the so-called superkick, offers the most dramatic illustration. When two spinning black holes merge, they emit gravitational waves. If the emission is asymmetric, as it is when the spins are oriented in particular configurations relative to the orbital plane, the radiated momentum is also asymmetric. The remnant black hole recoils by conservation of momentum, opposite to the direction of net radiation. In certain spin configurations, this recoil velocity can reach thousands of kilometers per second, sufficient to eject the remnant from its host galaxy entirely. What makes this remarkable is its origin. The recoil is not a classical force applied to the merging system from outside. It is a consequence of the geometry of the spacetime in the final moments before merger, encoding the angular structure of the inspiral into the gravitational wave emission pattern. The kick is what the rotating geometry of two merging black holes writes into the surrounding spacetime, carried away at the speed of light. The leftover object is flung across the sky by the imprint of its own angular history. The nested hierarchy makes this picture more vertiginous still. Our solar system is embedded in the gravitational field of the Milky Way. which is itself rotating. At the galaxy's center is a supermassive black hole whose frame-dragging effect extends, attenuated but non-zero, across galactic scales. The Sun rotates, the Earth rotates. Every one of these sources contributes, at some level, to the local inertial structure of every observer in the system. The local frame of any freely falling observer on Earth is shaped by the Earth's rotation, the Sun's rotation, the structure of the solar system, and the slow gravitomagnetic field of the galactic center, all simultaneously, all interlocked, none fully separable from the others. The nested nonlinearity of the field equations means there is no clean decomposition. The geometry is one thing, not many things stacked. In practice, the contributions from distant rotating sources to local physics near Earth are immeasurably small with any instrument we currently possess. The observation is about character, not magnitude. There is no level of the hierarchy at which the local definition of inertia is entirely disconnected from what everything else in the universe is doing. The shadow of a framework's precision. There is a way of reading the gaps in our treatment of frame dragging, the fact that it is rarely foregrounded, that the Kerr solution is rarely taught as the conceptually central result its geometry demands, that the nested hierarchical implications for local inertia across galactic scales are almost never discussed, that sees those gaps as pedagogical failures. The subject was there to be addressed. It was passed over. Something was lost. This reading misses something structural, and the miss goes deeper than charity. Physics gaps of this kind are the shadow cast by a framework's precision, and they are rarely failures in any meaningful sense. Every framework that works well enough to generate progress works precisely by choosing what not to describe. Newton's mechanics had to be successful enough for long enough for the perihelion precession of Mercury to become legible as a problem. The gap between Newton's prediction and Mercury's measured orbit was not a flaw in the Newtonian framework. It was the precise shape of what the Newtonian framework could not see, made visible only because the framework was precise enough to make the discrepancy measurable. The gap was a doorway. It opened inward onto general relativity. The gap in the treatment of FLRW cosmology examined in Before the Manifold Held follows the same logic. Energy density figures are quoted as thermodynamic scalars without their geometric content, because the FLRW framework earns its place precisely by describing the large-scale kinematics without describing what the manifold was locally doing. That choice of what to suppress is what makes the framework work at its level. The gap in our treatment of frame dragging is analogous. We do not routinely foreground the Machian implications of the Lenz-Thirring effect because the Newtonian treatment of inertia as a fixed background is precise enough for every practical purpose at terrestrial and solar system scales. Gravity Probe B required 6 years in orbit and engineering at the limits of what was achievable to detect 37 milliarcseconds of Lenz-Thirring precession per year. The gap exists because the effect, at the scales we most frequently work with, is not the thing that most needs to be said. But the shadow of a framework's precision is also where the next framework lives. And this gap between the treatment of rotation as a perturbation and its actual status as a geometric rewriting of inertia at every scale points somewhere. I want to examine that somewhere here, explicitly in terms of what is conjecture and what is established, and with no pretension that what follows is rigorous. The conjecture. In general relativity, the concept of force disappears for gravity. An object in free fall does not experience a gravitational force in any locally meaningful sense. It moves along a geodesic, the path of extremal proper time through curved spacetime. What we call gravity is not a push or a pull applied to an object by the mass near it. It is the geometry of the spacetime through which the object moves. The force has been replaced entirely by geometry. The other fundamental forces have not been treated this way. They remain in the standard model, forces, carried by exchange bosons, arising from gauge symmetries, characterized by coupling constants that measure how strongly a particle of given charge interacts with a given field. But they have each acquired, through the development of gauge theory in the 20th century, a geometric formulation. Electromagnetism is a U1 gauge theory. The electromagnetic four potential is a connection on a U1 principal bundle over spacetime. The field strength tensor, encoding the electric and magnetic fields, is the curvature of that connection. The strong force is a connection on an SU3 bundle, the weak force on an SU2 bundle. These are the mathematical structure of the theories, stated in the language of differential geometry. The forces differ in this language in the geometry of the space they inhabit, in what might be called their affinity rather than their coupling constant. The coupling constant is a number we measure. The affinity is the geometric fact the number is trying to describe. The conjecture, and I want to be explicit that what follows is a gesture rather than a claim, a direction pointed at rather than a destination reached, is that this is not incidental. The forces differ in the geometry of the space they inhabit because they are each, precisely, geometry. Electromagnetism is curvature in a U1 bundle. The strong force is curvature in an SU3 bundle. What we measure as coupling constants are descriptions of how a particle's internal degrees of freedom couple to a particular connection, how the geometry of the particle relates to the geometry of the field. The affinity is prior. The coupling constant is its shadow. If this is right, and it may not be, and the history of such speculation is littered with elegant gestures toward wrong answers, then the Planck epoch is the regime in which these manifolds become indistinguishable. The unification of forces at that density is a differentiation run in reverse, a single geometric object into which the distinct curvature structures of electromagnetism, the strong force, and the weak force can no longer be separately resolved, because the conditions that make those distinctions stable have not yet crystallized. The emergence of the separate forces in the cooling universe is a differentiation of a single geometry, the geometry acquiring finer structure as the conditions permit finer distinctions to hold. Kaluza-Klein theory attempted something structurally analogous in 1919, the electromagnetic field as the geometry of a compact additional spatial dimension, producing both the metric tensor of GR and the electromagnetic four potential from a single five-dimensional metric. It failed in various technical respects and was superseded by gauge theory proper. But its instinct was right, that adding the correct geometric structure produces the correct physics without separately asserting the existence of a field. The geometry is the field. What it pointed at was real, even where the specific construction was wrong. The question the conjecture leaves open, and this is the one I cannot answer, is whether the geometric and particle pictures are two descriptions of the same reality, or whether one of them is prior. In gauge theory, the connection is primary, and the field strength tensor is derived from it. In the particle picture, the gauge bosons are the primary objects, and the geometric language is a reformulation. These are not the same claim about what the world fundamentally is, even if they agree on every prediction. The conjecture points toward the geometric picture being prior. The basis for this is the history of general relativity. The theory that replaced a force with geometry proved more accurate, more general, and more structurally honest than the theory it replaced. The pattern, if it is a pattern, suggests the remaining forces are waiting for the same treatment. This falls short of a prediction. The machinery that would make it one does not yet exist. It is an observation about where the arc of geometric thinking in physics has been pointing, and a willingness to follow that arc further than the formalism currently allows. The shapes are behind the symbols. The question is which shapes?